Hello guys, welcome back to another video. In this video we will consider an integral from 0 to infinity sine of ax over divided by x dx. So we will consider an integral of I of y equals to an integral from 0 to infinity sine of ax divided by x e to the negative yx dx. We will differentiate this integral with respect to y, and what will we get? We will get an integral from 0 to infinity minus x sine of ax e to the negative yx divided by x. We will cancel out the x's and we are left out with an integral from 0 to infinity minus sine of ax e to the negative yx dx. This integral is easily solved by integration by parts. You have to do it 2 times in order to solve this one. Integration by parts. And you should get a result of negative a divided by a squared plus y squared. That's what you should get. Now we solve the integral in terms of I prime of y, which equals to this. Now we need to integrate both sides. So we get I of y is equals to minus a over a squared plus y squared dy. This is an easy integral which you can solve, which gives us minus arctangent of y over a plus c. What's interesting here is that we can find out what c is and we need it. So how will we do such thing? If we take a look at I of y, it's this thing. And if we make y go to infinity, in this integral will tend to 0. So for when y goes to infinity, we have 0 equals minus arctangent of y over a. It will be pi over 2. It doesn't depend on a. A is just a fixed constant, but it will depend on the sign of a. So we have a sine of a plus c, which when we solve for c is just pi over 2 sine of a. When we plug it back into our original integral, I of y, we get I of y that equals minus arctangent of y over a plus the c we just found out, so pi over 2 sine of a. And what do we need to find out is what is this integral. So if you can see, we set y equals to 0, we will have the integral we need to find. So let's set y equals to 0, so I of 0. Arctangent of 0 is just 0, so we will have pi over 2 sine of a. So that's what we got. Our original integral equals to pi over 2 sine of a. And that's pretty interesting. It means that for any a, if a is positive, we will have just pi over 2. So after we solve the first integral, we will consider this one. We solve the first one, and how will we solve this? So I forgot, it's 2x here, just to make it more interesting. We will write it out as 2. We will expand the sine of 2x into 2 sine of x, Let me write it a bit better. Sine of x cosine to the fifth of x divided by x dx. And how do you solve this one? Well, you can use the formula for the cosine squared. Cosine squared of x is just 1 plus cosine 2x. Sorry, it looks weird. Cosine of 2x divided by 2. So we can write the cosine of 5 of x as cosine. We can write this term like sine of x times cosine square of x times cosine square of x times cosine of x. And both of those you can replace with this, and then you just multiply the stuff out and use this formula. Sine times cosine nicely gives us sine of something, and we know what is sine of something over x. It's this formula we just derived. So I won't do the calculations because it will take too much time to solve the trigonometry. I will give you the result. You will get 5 over 16, an integral from 0 to infinity, sine of 2x divided by x dx, plus 1 over 4, an integral from 0 to infinity, sine of 4x divided by x dx. And now we have the last one, an integral, sorry, we probably have a constant, and that's 1 over 16, an integral from 0 to infinity, sine of 6x divided by x dx. Okay, so you just need to plug the values for this one, and we know the values for all of these integrals from this formula. A is positive here. It doesn't matter which number it is. It doesn't depend on A. It's just the sign of A. So we will have 5 over 16 times pi over 2. This is times, plus 1 over 4 times pi over 2, plus 1 over 16 times pi over 2. When you sum it all up, you should get 5 pi over 16. And that was the goal for this video. Alright guys, thanks for watching. Like, share and subscribe if you want to see more of this. And see you in the next video. Bye guys.